pleasure to introduce our speaker today. So we have our last seminar this semester and our last Dean Speaker lecture. Our Dean Speaker lecturer this day is Professor Mosher from Rutgers University. And so he's going to speak about hyperbolicity of the complex of free splitting here from Boston, Binghamton.
Thank you very much. Thank you. Hey, I'm coming up to Binghamton. I've come up twice before, I think.
At least.
And, actually, my favorite thing is something I hope to do tomorrow, which is to go prowling around back in your woods with all the beaver names.
Yes.
Beautiful place.
We're still
I
there.
feel like I'm wandering around in a Robert Frost poem back there. So I'm going to be talking about a theorem which is an attempt at generalizing, or not generalizing, finding an analog of the theorem of Mosher and Minsky. And what Mosher and Minsky proved is that the curve complex of a surface is hyperbolic. The curve complex is you have a surface and you take curves on the surface, and that's a vertex, well, up to isotopy. And you take two curves on the surface, and that's an edge, as long as they're disjoint. And it's connected, and the amazing thing is that this complex turns out to be a hyperbolic metric space using the simplicial metric, hyperbolic in the sense of Gromov. And this hyperbolicity has, many applications in the setting of mapping class groups, particularly aimed at trying to understand the large-scale geometry of the mapping class group itself. So there's been something of an industry in attempting to prove or disprove hyperbolicity of various out-of-Fn complexes. Those of us who were on the side of trying to prove hyperbolicity got this rude shock a couple of years ago when Lucas and Dima posted a paper proving that this splitting complex was not hyperbolic. It was like sent shivers through the world for a little bit. So we all thought about it and said, oh, okay, I understand why this is true. Okay. So on the positive side of things then, attempting to find analogs of the positivity of this statement is what we're going to try to prove, what we have proved. I'll mention also there's actually two theorems out there now. The one of Vesbina and Thane is that the free factor complex of a free group is hyperbolic. And then what I'm going to talk about today is my joint work with M.Handel, that the free splitting complex of Fn is hyperbolic. So let me talk about the free splitting complex. Let me talk about free splittings. Let me talk about curves. So what's a curve on a surface? I mentioned it briefly. So, here's a curve on a surface, okay? And this object here is going to be a vertex. Its isotopy class is going to be a vertex. Well, what's an analog of that for the free group? Well, let's just look at this a little bit more in the surface context. We can fatten this up, get a little annulus, and then what we can do is construct a dual graph of groups. And what we get here is a graph of groups where you have Z labeling the edge, which is dual to this annulus. The Z stands for the fundamental group of the annulus. And then you have this subsurface here. I don't know what to call this subsurface. Let me call it that subsurface. So here's a graph of groups decomposition of this sphere. Now, we find it more convenient ourselves to think in terms of the Bass-Serre tree. So the fundamental group of this thing is the fundamental group of S, or you can think of T, which is the Bass-Serre tree. And then the fundamental group of S is acting on that tree by Bass-Serre theory. Okay. So for us, a free splitting of Fn is an action of Fn on a tree T. So this is a simplicial tree. The action is simplicial. The action is minimal, meaning that no proper subtree is invariant under the action, and edge stabilizers are trivial. Okay, that's the free part of it, as opposed to over here, in this case, edge stabilizers are infinite cyclic. Now, I say that we do tend to think in terms of the trees, but you can also, it certainly helps to visualize these objects by thinking in various other terms. So you can think of the quotient graph of groups. There's other models which are useful for taking advantage of your geometric intuition. There's the model of a sphere complex in a certain three-manifold, which is constructed to have Fn as its fundamental group. That's very strongly analogous to the curved complex of this surface, which is constructed to have fundamental group pi1 of S. So let me give you then some pictures of quotient graphs of groups, primarily not because that's how we think, but as a way of visualizing the free-splitting complex. So let's start off with a vertex. Well, first, the equivalence relation. So Fn act on T and T prime are equivalent if there exists an Fn equivariant homeomorphism. Alrighty. So now I'm ready to talk about the free-splitting complex. So first of all, the zero simplices.
Could you translate that to a three-manifold setting, or does that translate easily?
It does translate. It's just isotopy classes of sphere systems. That's all it is. There are definitely things you have to be careful about when you attempt to translate, but that's not one. You can sort of be crude about that one and just say isotopy classes of sphere systems. There are cases where you have to actually be careful and say homotopy classes versus isotopy classes, which you don't have to be in the certain situation. But just defining for single spheres, you could just say isotopy classes. Once you start talking about multiple spheres, then it gets tricky. Okay, so what are the zero simplices? The zero simplices are one edge free splittings, which is to say that the quotient graph of groups can look like this. Here's Fk, and here's Fn minus k, and you connect them by an edge. And this is just the picture that we all learned to draw for a free product. So a free product of an Fk and an Fn minus k. Now, I'm being somewhat crude here. I don't actually mean this to represent any particular rank k free product or rank n minus k free factor, because part of the problem that I dislike about thinking the quotient graphs of groups is that you actually have to keep track of the isomorphism between the fundamental group of the graph of groups and the Fn itself, and equivalence relations of isomorphisms. You actually have to sort of stare at the, if you're going to think in terms of quotient graphs of groups, you actually have to stare at the sort of, at Serre's definition of pi1 of a graph of groups and make sure that you have the correct equivalence relation and so on. So the quotient graph of groups is definitely a pain. It's definitely easier to think in terms of either sphere complexes or just in terms of trees. So this is one type of zero simplex. Another type of zero simplex is like that, and this is the typical amalgamated free product situation, where here you have a rank n-1 free group, and then you have a stable letter, and you're just, well, you're amalgamating the trivial group over itself. So you could, of course, rewrite this one as one of those kinds, but these are different free splittings, okay? Algebraically, they contain the same information, but we really think of free splittings geometrically in terms of these actions on trees. Okay, so let me show an example of a one simplex. So for instance, I could start out with this free splitting here, and then I could blow that edge up. So I'll blow that edge up. And so over here, I'll have an Fn minus k minus, this is an Fn minus 1, and this is an Fk. Okay, so in this one here, I have this blue edge, which I collapsed to give me that graph of groups. I could alternately decide to collapse that red edge, and then I would have a different free splitting like that, okay? Again, it's just, you know, here's a rank n-1 free factor, and here's a different rank n-1 free factor, and these are actually different free splittings here. So there's an example of a one simplex, and I could, you know, I could go up to a two simplex. I could take that vertex there and blow it up. So now I have an Fn minus k minus 1, and then here I have an Fk minus a, and here I have an Fa, and then I could, you know, I could sort of fill out the whole picture here. And there would be a picture of a two simplex.
So you're saying there's no equivariant at the level of trees, the two extreme white ones on top, there's no equivariant homeomorphism.
There is no equivariant homeomorphism.
Even though both of them have a single orbit in one side.
Exactly. These are in the same orbit of the action of out of Fn, which is to say that there's a twisted equivariant homeomorphism between them. Okay? Okay. Now, I've drawn this picture, you know, zero simplex, zero simplex, zero simplex, one simplex, one simplex, one simplex, and two simplex. But to tell the truth, what we really do is we work in the barycentric subdivision. Okay, so that's what I'm going to use as the free splitting complex. Fs of Fn is the first barycentric subdivision of the ordinary free splitting complex. And it has a very interesting advantage, which is going to be used in a crucial place in what I tell you about.
Sorry, did you ever say what an edge is? I'm sorry, did I miss that?
An edge is a zero simplex is a one edge free splitting.
Yeah.
And a one simplex is a two edge free splitting. What the hell is a 3L llama? You could go ask your mama. A two simplex is a 3-edge free splitting and so on.
I see.
Okay?
Is there
So a k-simplex is a k plus 1 edge free splitting up to equivalence.
Is there a very brief way to explain the key difference between this complex and the free factor complex?
Well, the free factor complex ignores the edges and just remembers the stabilizers. So the information of how the edges are attached is entirely lost, and there's a lot of stuff going on there. There is a simplicial map. The edge forgetting map is a simplicial map, and the fibers of that map are complicated beasts. Okay, so I'm actually going to work in the first barycentric subdivision, where now so in the first barycentric subdivision, which is the last time I'm going to say those words, Fs of Fn, a zero simplex is any free splitting up to equivalence, and a one simplex is a collapse. So here's a one simplex of the first barycentric subdivision. It's a collapse. Here's a different one simplex of a barycentric subdivision. It's a collapse. Here's a one simplex of barycentric subdivision. It's a collapse. Okay? So a one simplex is a collapse from one free splitting to another.
So all the one simplex are automatically has a sort of orientation.
Yes, one simplices are oriented. And a concatenation of two oriented one simplices is, if I collapse first the white and then the red, then I can take a shortcut and collapse them both simultaneously. Okay? So collapse is transitive. Collapse is transitive. And this has an interesting implication to the local geometry, which is that geodesics in the free splitting complex cannot have two collapses in a row, because you could always shortcut it. So a geodesic in the free splitting complex has a structure of collapse, expand, collapse, expand, collapse, expand, collapse, expand. It alternates collapse, expand, collapse, expand, collapse, expand, collapse, expand. This is actually a feature of any first barycentric subdivision. The geodesics in any first barycentric subdivision have this collapse expand structure.
I'm sorry, I must have been writing the meaning of the phrase "they are oriented." Could you just say again what that means?
A collapse is a map from one free splitting to another free splitting.
Right.
So it induces an orientation of the edge, where the orientation points from the domain of the collapse to the range of the collapse. Okay. So, I want to sketch for you a proof that the free-splitting complex is connected. Because it introduces, this proof introduces one of the key concepts in our approach to analyzing the free-splitting complex, namely the concept of Stalling's fold paths. So I'm going to prove connectivity. Free-splitting complex using Stalling's fold paths. Okay. All right. So here's a free-splitting S, and here's a free-splitting T, and I'm looking for a path in the free-splitting complex from S to T. And the idea of constructing this path, well, I mean, this is an actual geometric object. It's a tree with the free group acting. Another tree with the free group acting. I'm actually going to pick an equivariant map if I can. So, given S and T vertices, I want to pick an equivariant map from S to T, and then I'm going to factor it into small pieces. And that's how I'm going to prove that, that's how I'm going to construct an actual path. I'm going to factor this map F into a map F1, and a map F2, and so on. Here's Sk minus 1, Fk, here's Sk. And these factors will be so small that I'll be able to see, obviously, there's a path from here to there. And obviously, there's a path from here to there, and so on.
So how do you know there is an F?
Good question.
I mean, doesn't that make them equivalent or something?
No, that would be an equivariant homeomorphism.
Oh, you mean map when you say map.
I just mean an equivariant function. Continuous. Not continuous. These are trees. And there's a lot of freedom in constructing equivariant maps between trees. For instance, this tree has a vertex. Pick its image. And then that forces what happens to the image of its entire orbit. If V goes to W, then f of V must go to f of W. And there's only finitely many vertex orbits, so do that for every vertex orbit. I've now defined the map on vertices. Well, every edge, its endpoints are already defined, and so I just extend that to a path over here. This is a tree.
So you pick a representative of each orbit,
Correct.
say where it's to go, and then extend equivariantly
Correct.
on the vertices.
Correct.
And then you go to the edge, and that's well defined? I mean, I haven't thought this through. Is that well defined?
Well, there could be problems. There could be problems. So, for instance, suppose you picked a vertex which was stabilized by Fn minus 1. And suppose this tree didn't have any vertex stabilized by Fn minus 1. Then it's impossible. There is no F. So that's the first obstruction. S could have a non-trivial S could have a subgroup of Fn, which is a vertex stabilizer. But this subgroup does not stabilize any vertex of T. exist. Well, who cares? Because I can blow up the vertex stabilizers. And blowing up a vertex stabilizer just moves me along an edge, and I'm just trying to prove connectivity. And so I'll reduce all the ranks of the vertex stabilizers, and if there's still some non-trivial ones, I'll blow those up. And I'll keep blowing them up, maybe moving along edges. Actually, I can blow them all up in one edge. So there's one edge from S to S prime, so that in S prime, all vertex stabilizers are trivial. And now, even if I couldn't have defined the map from S to T, I can define the map from S prime to T. Okay? All right, so as long as I'm happy to sort of move distance 1, then I can get this map F. Now, I want to factor this map, and I want to tell you how to factor this map, but in order to be able to do it in a way that works nicely, I need this F to have a certain property. So this is the definition of a foldable map. F is foldable if every F is injective on every natural edge of S prime. When I use the word natural in this context, trees can have, a minimal tree won't have any valence 1 vertices, but it could have valence 2 vertices, and that's, even though we have to allow valence 2 vertices, we sort of turn our nose down on them, and we declare them to be rather unnatural creatures. So natural just means an edge whose interior endpoints, whose interior vertices are all valence 2, and whose boundary vertices are valence 3 or higher. So this is a picture of a natural edge. Okay? So the restriction of F to any natural edge is supposed to be injective. And the second thing is that for every natural vertex V, so here's V, it has at least 3 directions. It may well have, it has at least 3 directions. The image of the derivative of F has cardinality greater than or equal to 3. Okay? And the derivative is just what you think. I mean, here's F of B, and every one of these edges has an image direction. But it's possible that several edges might have the same image direction, and these edges might have that image direction, and these edges will have that image direction, and these edges will have that image direction. So that's 4 image directions that I'm safe. Okay, so this is the definition of a foldable map. Now, foldable maps might not exist, but then there's just one more thing that you have to do, which is maybe collapse some stuff out after maybe more collapsing exists. For instance, you might have unluckily taken two vertices of S to the same point, connected by an edge, which is getting crushed to a point. It can't be injected. So you might be forced, after being forced to blow some stuff, you might be forced to blow other stuff down. And the proof of this is there's sort of an optimization argument here, but that's a real technicality that I don't want to get into. So this is just a lemma. But this lemma allows us to define the folding process. So now I can define F1. Here's how I define F1. I take a vertex of S0 and I ask myself, does it have two directions which have the same image direction? And if it does, then what I do is I fold those together. Now, there may be many very complicated identifications from S0 to T, and what I do is I'm doing the identifications just a little tiny bit at a time. I look just locally for this identification, and if I see it, I make that identification. And I make it maximally. This is called a maximal fold. And that defines S1. So this was a technique. It's first sort of described in detail and applied and exploited by Stallings, which is why these are called Stallings fold sequences. And a simple induction argument shows that this has to stop when you get to T. And then a simple sort of topological argument shows that the distance from S0 to S1 is at most an expand followed by a collapse. So the distance from S, this is double prime, to S1 is less than or equal to 2. So moving distance at most 2 to S double prime, and then a single fold distance at most 2, another fold distance at most 2, finitely many of them, you get to T, and that's the proof of connectivity. Okay. So, these paths that you get, a Stallings fold path in the free splitting complex is any sequence of this kind. S0, S1, S2, Sk of this kind. So to call it a path is a little bit of a stretch because I'm not necessarily insisting that these be endpoints of an edge. You have to sort of take a look at this proof to see how this distance 2 can actually occur. So these are sort of coarse paths. In that instead of just having jumps of distance 1, I could have jumps of distance 2. All right. But what this lemma demonstrates, or what the proof of this lemma demonstrates, is that the collection of Stallings fold paths, so a corollary of the proof is that the collection of Stallings fold paths is coarsely transitive. In the free splitting complex. What that means is if I take any two vertices, then by moving the first vertex distance at most 2, I can then find a Stallings fold path, and the jumps are all distance at most 2. Okay. So now I can describe the scheme for proving hyperbolicity. And
This is a k minus one dimensional, sorry, n minus one dimensional complex, this thing?
it is, but we're ignoring, just going to work with the one skeleton.
I see.
Okay, I mean, hyperbolicity is,
Yeah.
you know, qi invariant. As long as you have a connected complex, then you're safe using the one skeleton, except that we are using the one skeleton of this barycentric subdivision specifically.
It's higher dimensional than that, though, right?
Oh, sorry.
I said n minus one dimensional.
The dimension is, take a rank n graph where every vertex has valence 3. So in rank 2, you could have 2 vertices and 3 edges. Okay, and then each time the rank goes up, you stick in 2 points, so you add 2 edges. So that makes it, okay, so in rank, so it's 2g minus 1, 2n minus 1.
2n.
Well, and then you're projectivizing because it's a simplex, so it's 2n minus 2. Does that sound right? Am I getting that right?
It went too fast for me, but I'm sure.
Okay. So it's not just n, it's like 2. Yeah, every time you, to go up a rank, one edge is subdivided at 2 points and another edge is put in. Oh, so one edge becomes 4, one becomes 4. So it's 3g, it's 3g minus some constant.
And this is not locally finite, or is locally finite?
It is not locally finite because you can have these vertices with stabilizers that can be blown up in infinitely many different ways. The zero simplex has infinitely many adjacent one simplices because in that tree there is a vertex which can be blown up in infinitely many different ways. Okay, so the scheme is to use the Mosher-Minsky axioms. The Mosher-Minsky axioms say that a connected one complex X is hyperbolic if there is a coarsely transitive path system such that blah, 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 axiom 1, axiom 2, axiom 3, and so on. 1, 2, 3, and so on, okay? And what these axioms say that you need to know for the moment, they say that the paths in this system behave the way uniform quasi-geodesics in a hyperbolic space ought to behave. Now, so this is how we thought about the problem. I mean, we knew that Mosher-Minsky axioms, and we knew we had to prove them, and to prove them, we just thought of the problem in this way, and as soon as we actually had enough gut feeling for, yes, these Stallings fold paths sure do seem to be behaving like uniform quasi-geodesics in the hyperbolic space ought to behave, maybe we should actually try proving the axioms now, and that would sort of guide us along as we went along. And a lot of that was sort of course, not nearly as explicit as that because you never know what you're doing. You're just bumbling along usually. And then it's all after the fact. So, hey, that was a kind of non-positive curvature behavior. Oh yeah, it was. So that's the first thing. Some non-positive curvature behavior. the combing lemmas. Let me give you the first combing lemma. Given a Stallings full path, S0. Now I'm going to put arrows in here rather than just commas. And when I put arrows in, I mean that I've actually picked the functions, the F1 and the F2. And a collapse map and this will be the portion that's collapsed, begin collapsing an edge, begin collapsing two edges, and so on. And really, of course, these collapse maps are equivariant, so I'm collapsing one orbit of edges or two orbits of edges. There exists a commutative diagram. So T equals TK. I stick in an SK minus 1. Here's the TK minus 1. Here's the T2. Here's the T1. Here's the T0. Here's collapse maps. Beta K minus 1, beta 2, beta 1, beta 0. There exists a commutative diagram where the bottom row is a fold sequence. Where the bottom row is a fold sequence and all vertical maps are collapse maps.
Do you require the T's to be distinct?
Well, okay. The bottom row is a fold sequence, with maybe some equivalences, homeomorphisms thrown in as well. Okay, and vertical arrows are collapses. Okay, and I said this is a commutative diagram. Good. Commutativity of the diagram can be translated into a statement about the relationship of beta 1 to beta 2. The beta 2 subgraph, which is collapsed here, pulls back to the beta 1 subgraph, pulls back to the beta 0 subgraph. So this diagram is actually completely determined just by the top row and the beta k. And everything else is just filled in by pulling back and collapsing. These maps are determined. It's all completely automatic. And this is a kind of combing behavior. This is the kind of thing you like to see in hyperbolic groups. If I can get from A to B by a quasi-geodesic, and then I move B a short distance, then I should be able to get from A to this, so B to B prime, I should be able to get from A to B prime by a quasi-geodesic as well. Or maybe I'm willing to allow myself, if I go from A to B and then I move B to B prime, as long as I'm willing to move A to A prime, I can get there by a quasi-geodesic in my path system. So that's what this is saying. It's a kind of a non-positive curvature condition, a kind of combing condition. This is not negatively curved per se, because this happens, this kind of combing behavior happens, for instance, in Euclidean space. Okay. So this proof, I've actually given you the proof. You take the betas, you pull them back, you collapse, you take the induced maps. That's the proof. It's very easy. There is another version of it, though, which says, given a Stallings fold path Then I want to do the same thing. I want to pull this back. The statement is pretty much exactly the same with a few caveats. There exists, the caveats is that I'm not going to call it a full path anymore. In fact, I already had to stretch the truth a little bit by allowing equivalences. So there exists a commutative diagram of foldable maps. These maps up top might be larger than single folds. Foldable maps and collapses. So we were using these two lemmas long before we realized they were lemmas. We were just sort of doing these kind of combing operations all over the place when we were working on this problem early on. And at some point, one of us said to the other, look, we got to prove this. It's like, I don't want to prove this, you prove this. I don't want to prove this, you prove this. So this first one is easy to prove. The second one was a pain. And the proof of this second one underwent many, many changes. And it's by far more technical and annoying. And that's why I'm not going to talk about it.
But this is, it can be somehow extended to an actual fold path.
It can,
You can
by,
interpolate in between.
you can interpolate in between. What's more important is that when you do that, actually the diameter of this whole interpolating portion is bounded. Okay?
By 2 or something.
No, it could be larger than that.
Well, is it uniform or
Yes, it's uniform.
depending on in or?
No, it doesn't depend on, oh yes, depending on, yeah, it's typically, we're going to see this behavior actually in a little bit, in when I get to the heart of the matter, which I'm actually just about to get to. But yes, there could be arbitrarily many actual folds in here, because what can happen is that what beta is doing is taking a vertex with a high-rank stabilizer and blowing it up. And then you pull that back, and the pre-image vertex has that same stabilizer and is getting blown up. And now this tree and that tree have to be mapped to each other, and there could be arbitrarily many folds. But as you map that tree to this one with arbitrarily many folds, all the edges outside that tree are just sitting there watching this go on. And those edges represent a constant distance of a free split. Okay.
Do you have a name for that?
For what?
That top path?
Oh, this is, we have a name for these two processes. This process here is called combing by collapse. You have a fold path followed by a collapse and you comb it. And this process here is called combing by expansion. You have a fold path here and then you expand. All right. Now, if you were looking for hyperbolicity, this would be entirely unconvincing because it's not a hyperbolicity property per se. It's just a non-positive curvature property. So now we need to look for an actual hyperbolicity property. Okay, so here's what we're going to do. We're going to start with an input, which is a Stallings fold path. And then, off of this vertex, we're going to take a geodesic in the free splitting complex. We're going to collapse, we're going to expand, and collapse. And expand, and collapse. What do I want? No. I want to start with the collapse instead. We're going to collapse, and expand, and collapse, and expand, and collapse, and expand. So let's see, this will be R0, and this is R1, R2, and R3, and R4, R6. Okay, so there we go. So we're starting with a collapse. We will apply the combing by collapse lemma, and we get oops, my arrows went the wrong way. We apply the combing by collapse lemma, and we get this full double sequence. Okay? Now, this generalizes to foldable paths, sequences. And this generalizes to foldable sequences. That's one of the things that makes this a little more technical. In other words, what's a foldable sequence? Well, every horizontal map that you can imagine from S1 to S3, from S2 to S47 is a foldable map. Just a way to generalize Stallings fold paths so that we can do this. Okay. What next? Now I shall do combing by expansion. And what next? I shall do combing by collapse. And then I shall do combing by expansion. It's looking bad for hyperbolicity. Hyperbolic spaces are not supposed to have big fat rectangles.
There are reverses, right? Every time.
Mm.
You have to have no vertices every time when you go.
Nope. Nope.
You start from a fold, but then, just as you say here, you have.
Well, okay, yeah. These individual jumps here could maybe are factored themselves. Okay, but even so, I shouldn't have this kind of rectangle here. Okay, I really shouldn't.
And the distance is uniformly bounded by this.
Every time when you go to the next level.
Oh yeah, that could get worse. Yeah, that could get worse. You know, this path length could be longer, and then this path length could be longer. That kind of thing could get worse. But even so, I mean, this path is a quasi-GD. When I subdivide it, and then when I subdivide this one, you know, into individual folds, those paths are supposed to be still quasi-geodesics. So, you know, this rectangle picture just shouldn't exist without something happening. And what's supposed to happen is that it's all supposed to squish together. Okay? If you have a quasi-geodesic here, and a quasi-geodesic here, and a quasi-geodesic here, and all these parallel quasi-geodesics here, it's not supposed to look like this without the distances collapsing in the middle. And that's what we have to show. So, the key technique is to start from this diagram right here. Collapse, expand, collapse, expand. 4 in a row of a geodesic, and to stare at it and to say, what property does this sequence of collapse, expands, have that correlates to being geodesic? How can that property fail? How can I force it to fail? Because as I pull back, I still have collapse, expand. And as I pull back, I still have collapse, expand. And when I get into the middle, I may have started with a geodesic here, but there shouldn't be a geodesic in the middle. There should be some distance contraction going on in the middle. So this is what it comes down to, is studying. It's as simple as you just simply study sequences of length 4, collapse, expand. When are they geodesics? When are there shortcuts? So this leads to a W diagram. S0, collapse, S1, expand, S2, well, R. R0, collapse, R1, expand, R2, collapse, R3, expand, R4. Now, these are free splittings. R2 goes to R1, is collapsing a blue subgraph. R2 goes to R3, is collapsing a red subgraph. Okay? And the main observation, well, the first observation, is that if R1, R2, R3, R4 is a geodesic, then R2 is equal to beta union rho. In other words, here you have this collapse, expand, collapse, expand. You look in the middle, there's one tree collapse this direction, there's one tree collapse that direction. If they do not fill up the whole tree, if beta and rho, their union is not all of R2, then there's a shortcut. Okay, so that's going to be the proof, and I'm going to show you the shortcut. If R2 is not equal to beta union rho, then there is a shortcut. Oh, I have to add W diagram. Let's assume that beta and rho are natural subgraphs. That's a safe assumption whenever I have a path like this, and whenever I have a collapse, maybe my natural cell structure has been finely subdivided into little itty bitty edgelets, and maybe beta is a subcomplex of this fine subdivision, but the effect of a collapse is unchanged by restricting the natural subgraph. So let's assume that these are natural subgraphs, but they are not equal to R2, then there's a shortcut. So what's the shortcut? The shortcut is you collapse rho union beta. Okay? If rho union beta were the whole thing and you collapsed it, you'd get a point, and that would be bad. You wouldn't have a free splitting. But if rho union beta is a proper equivariant subgraph, then you can collapse it. And you go all the way from second base to home plate, and then you can go the long way from second base to first base, collapsing the beta, and then you can go the rest of the way by collapsing the part of rho that was not already collapsed, which is rho minus beta. And then you can also go the short way again, straight to home base, or you can go first collapsing rho, and then collapsing the part of beta that was not already collapsed. And then you use the observation that a composition of two collapse maps is a single collapse map, and you constructed a shortcut. Length 2 path instead of a length 4 path. So now we're ready for the second observation. So let's see. I can change my notation a little bit. This is, the superscripts are going to be the row numbers, and the subscripts are the column numbers. Okay? So this is R0J, R1J, 2J, R3J. Collapse, expand, collapse, expand. And here we have beta K is the blue graph that's collapsed there, and then that pulls back all the way to beta J. And then here we have row K, which is the collapsed graph there, and that pulls all the way back to row J. So I have a W diagram in column K, and then I'm pulling that back, and then a W diagram in column K minus 1 and column K minus 2, and all the way back to column J. And then here's the second observation, and this is really the key observation. I want to weaken this assumption. What this first observation actually proved is that if this is a geodesic, then R is the union of the maximal natural subgraphs of beta and rho. If not, you pass to the maximal natural subgraphs. So there's a little technical step there. So now I'm over in this situation. I'm starting with, as I said, a geodesic. Starting with a geodesic on the right-hand side, we know that the beta K and the rho K, their maximal natural subgraphs fill up all of this tree. Starting the assumption that column K is geodesic, R2 is the union of the maximal natural subgraphs of beta K and rho K. And so now that we say, all right, suppose we are in the unfortunate situation that this property remains true in column K minus 1, that R2K minus 1 is the union of these maximal natural subgraphs. And in this column, and in this column, and in this column, and in this column, and all the way back to here. Suppose also that in column J, R2J is the union of the maximal natural subgraphs of beta J and rho J. That would be the bad situation from a perspective of hyperbolicity. We would not be seeing the kind of distance contraction that we need to see, at least going back to J. Okay? The conclusion is that this whole portion of the original Stallings fold path has bounded diameter. So the diameter of Sj plus 1, Sk minus 1, Sk is bounded by a constant depending only on the rank of Fn, which is n. In fact, we can write down an explicit constant. It's something on the order of n, sort of constant times n squared, something like that. So the way you use this then is you construct these big rectangles, and moving back a bounded diameter, everything to the left, 4 rows collapses to 2. And then you take the next 2 rows up. Moving back a bounded diameter more, those 4 rows collapse to 2. And then you take the next 2. And so you move back these units of distance. We call these units free-splitting units. They are, it's not just bounded diameter, it's a particular way of achieving bounded diameter. So by moving back a bounded number of free-splitting units, you get you get sort of distance 2 contraction to the left of that, and moving back another bounded chunk of free-splitting units, another distance 2 contraction, and so on and so on. And that is exactly the kind of hyperbolicity behavior that you need. And then once you have that, you start proving the Mosher-Minsky axioms with it. I'm out of time. This is actually rather explicit, and I can explain this in more detail exactly how to get this bounded diameter estimate here in this context. And it's actually very mechanical. It's so mechanical that I'm completely convinced that we can actually write down a delta for the hyperbolicity complex, but I haven't done it yet. So I should quit.
Any questions?
I have a broad question, not about your detailed proof, but so once you have this graph on which the outer Fn acts, which is hyperbolic, what do you do with that information?
Well, okay, so, we know what to do with that information in the context of mapping class groups where we have a lot of structure, a lot of applications of it. We don't have any of those applications in place yet in out of Fn.
So perhaps in my ignorance I should ask you just very briefly say what you do in the case of the mapping class group.
So, one example in the case of mapping class groups is that there's a theorem of Vespina and Fujiwara that says that whenever, actually, okay, here's an honest application of this guy. Whenever you have a group that acts on a hyperbolic metric space, as long as that action has some type of tameness behavior, sort of some kind of behavior, it goes under the word of acylindrical, although that's too strong, then you get lots of quasi-morphisms, and you can then construct construct lots of examples of subgroups whose second bounded cohomology is, infinite dimensional, the kind of thing that happens for non-elementary hyperbolic groups. This is exactly how Vespina and Fujiwara prove that any non-elementary subgroup of mapping, virtually abelian subgroup of mapping class groups has unbounded dimensional has infinite dimensional second bounded cohomology. This complex is not enough to prove that for arbitrary subgroups of out of Fn. but it does prove it for a whole new chunk of subgroups out of Fn. It proves it, the Vespina and Fein one does that as well. Our theorem actually catches a wider collection of subgroups for which we can verify unbounded dimensional second cohomology. I'm getting my words all mixed up.
But if I carried away from, your answer was interesting, but if I carried away from it the fact that having a hyperbolic metric allows you to construct quasi-morphisms, is that the philosophy?
Huh?
Is that what the philosophy is
Yes,
about?
that is
Construction
exactly
of
what the plot. That
quasi-morphisms.
goes back to was it Bob Brooks who first did this in the hyperbolic plane? I think that's the right name. And then was generalized to higher dimensions and then to word hyperbolic groups and to mapping class groups and many other situations. So mapping class groups by virtue of the hyperbolicity of the curve complex.
And you actually construct these quasi-morphisms, or is there some abstract compactness argument?
No, you actually construct them. It comes from the fact that in the hyperbolic plane, it comes from the fact that if you take a triangle and you take, say, you parallel translate a tangent vector around this whole triangle, the worst it can do is rotate by pi. And there's the error term of the quasi-morphism. So you take three group elements, G, H, and I guess GH inverse, and you construct this quasi-morphism by placing those 3 points. This is a group acting, this is a Fuchsian group, by placing those 3 points and watching the parallel translation of that tangent vector, which is at both pi, and that's the error term in the quasi-morphism, and that's how Brooks proved that a Fuchsian group has infinite dimensional second bounded cohomology. And so that proof, of course, there's no parallel translation in general Gromov hyperbolic metric spaces, but then you coarsify that proof, and it works in general. And then it works. What Vespina and Fujiwara discovered was that it works whenever you have a sufficiently rich action of a group on any hyperbolic metric space. A sufficiently rich collection of actions on hyperbolic metric spaces. So there's one example. There are, that's the one that I can mention, which is, it's not immediate just from our proof of hyperbolicity. What you have to do is you then have to go ahead and characterize, well, you ask which elements of the group act loxodromically, and then which pairs of loxodromic elements have independent axes. Once you have a pair of elements with independent axes, then you can run this whole Brooks type argument and get lots of quasi-morphisms.
Which is your next paper.
Yeah.